pleasure to introduce our keynote speaker. And Mark is one of those persons that his CV is too impressive to summarize. So if you don't mind, I'll just mention a couple of things. So Mark is a professor in statistics at Imperial College in London. So he goes for the London Mafia. And is also one of the program director at the Alan Turing Institute, which is the National Institute for Data Science. I think recently closed a £10 million research grant with the Lloyd Register Group to work on data-centric engineering. So that sounds pretty exciting. So hopefully we'll hear a bit more about that. Thanks, Mark.
And thanks very much for the invitation to come here. This is a really great initiative, I think, and I'm hoping to get one of these cool T-shirts by the end of the day, Cambridge Spark T-shirt. So, data-centric engineering. As Raoul mentioned, we have this program at the Alan Turing Institute on data-centric engineering. And one of the questions always is data-centric engineering just another bandwagon that's rolling along, similar to big data, data science, AI, and so forth? Is this just hype? Or is there some substance in this and some hope in this? And so what I'm going to try and do is answer that question and kind of mingle it in with a description of the program and some of the things that we can actually achieve by taking a data-centric engineering, a data-centric approach to engineering. So what about hype? Well, some of you that are interested in the history of engineering would say, look, Lord Kelvin, the great Victorian physicist, there's no... Oh, this must be one of the cheap ones where there's no laser with it. Doesn't matter.
There's no laser.
Okay. You need to increase your budget then. Is it? Oh, well, they need to increase their budget. And so Lord Kelvin was the polymath Victorian physicist and engineer. He was instrumental in laying the first transatlantic communication line under the sea. And what he said was, to measure anything is to know it. And if you cannot measure anything, something that you're studying, then you cannot improve it. And one could argue that data has been absolutely central to all of the engineering sciences for the past couple of centuries. And I would say that in fact is the case for all empirical sciences or all observational sciences, that data has always been at the core. And therefore, the phrase data-centric engineering isn't really telling us anything new. And for that matter, data science isn't really telling us anything that's particularly new. Well, that's the argument against. What's the argument for? Well, before I make the argument a little bit more slowly than the argument against, let me just introduce the Alan Turing Institute. So it was instituted in 2000 and, well, discussion started off in government around about 2014 to set up a national institute for data science. And 2015, the government decided that it would indeed fund and support the establishment of this institute. And for the last 12 months, the institute has now been up and running and trying to get an agenda for the national data science space. But around about the same time the government were discussing what the UK should be doing about data science, the Lloyd's Register Foundation had commissioned a technology report about the impact that big data would have on engineering. And that report was published in 2015, and the foundation made a strategic decision that they would partner with the UK's Institute for Data Science and would initiate a program of research, translation, education, and commercial activity on data-centric engineering. And so I was appointed director in January this year. And so this last 10 months has really been taken up in establishing the program, recruiting people, initiating projects and programs and collaborations with various key industry and industry partners. And the three main challenges, grand challenges that we've set ourselves and for which everything that we do is focused on are the following. How do we make a resilient infrastructure for all urban environments? How do we monitor very complex engineering systems? And when I talk about engineering systems, I talk about systems that interact with people, with communities and so forth. So not just a gas turbine or what have you. How do we monitor these complex systems for events that may well have high consequences and typically are rare? And then how do we exploit data to revolutionize the design process? And so those are the three main challenges that we've set ourselves and are basically the concentration points for all of the activity that we're developing. And there is a lot of activity. It's very exciting. Today, for example, the Mayor's Office of the Greater London Authority are going to announce that they're funding a collaboration with the data-centric engineering program at Turing to try and improve the air quality around London by the use of data from the monitoring stations around the city. Next week, the Times are going to be running a story on I keep thinking this has got a pointer, but right down at the bottom, you'll see that one of the projects that we are leading, in fact, is the world's first 3D printed pedestrian bridge, printed steel bridge, which is going to open up in Amsterdam. And our data-centric engineering program are doing things like developing sensor networks, video-based methods to actually assess the scenes on the bridge, developing digital twins, and so forth. And so the Times, they interviewed me, they took a video of some of the things that we're doing on this, and that again is going to be released on Monday, so that's the 23rd. And in addition to those sort of highlights at the moment, we're working with, well, you can see many of the sort of collaborators, Thames Water, National Grid, London Underground, or Transport for London in general, large corporations like Shell. We're also working with government departments, the Health and Safety Executive, the Home Office, and on it goes. And if you go to our website, you'll actually see some of the things that are ongoing. I just want to give you a little snippet. But what I want to show is that what we're interested in, what as the director, what I'm really interested in is not just doing great research that gets published and 2 or 3 people read it and that's it. We really want to translate that work to commercial products, to commercial services, to really make a difference. And here's an example, a successful example of some work. This was with a company called National Cash Registers. And probably up until now, most of us use these on a daily basis. I used to certainly take cash out from an ATM, which was usually an NCR machine. Now, however, I use my mobile phone to pay for everything. So maybe the day of the National Cash Registers ATMs are slightly numbered. But NCR is a very historical company, been running for over 100 odd years, and unsurprisingly, their main products were cash machines. NCR was the precursor to the mighty IBM. Their main products, their main services or financial services and financial transactions for banking systems, and so the ATM is probably the most visible one. Now, there was a commercial challenge, and the commercial challenge was fraud. So it turns out that ATMs that recycle cash that has been deposited in them. Now, when I say recycle, what I mean is that you can deposit some cash, and the cash that's been deposited can now be used for withdrawals. Okay, so there is no manual intervention in checking the validity or the of the cash that's been put in to these machines. And subsequently, this means that this is an ideal way of laundering counterfeit cash and actually getting it distributed into a local economy. And so NCR came to me to say, we have a commercial opportunity here. If we could have a currency validation unit in our ATMs, then the whole of the Far Eastern market would absolutely pick up on this. And if we could do this, in a way that would be flexible, so that it could be deployed by various banks in various countries without any pain and additional cost, then we could really make some money here. So the sort of standard technologies that are used are ones which banks will typically employ, and so you have these security features, which, like watermarks and so forth, which again are typically used by banks when some sort of semi-manual process is being used. So money would be deposited and it would then be taken to the bank and checked. So this is a manual intervention which really we wouldn't want. So we would want to have completely automated counterfeit detection. So we want the verification and the validation to be automated. We would want to be able to support a huge amount of diversity of banknotes and of currencies, and of course the quality of those notes. The geographic variability of the quality of the notes will depend on the sort of typical weather that you would see, depending on whether it's a very humid environment or a very dry environment and so forth. The intelligence or knowledge, characterization of counterfeits is very limited, and in fact it's non-existent. And the typical existing paradigm that's used in data science or machine learning, supervised learning you would say, requires that we have representative samples of both genuine and counterfeit notes. And this, of course, is something that we don't have in reality. So standard existing products, in essence, use a handcrafted template. And as soon as new currency or new features are introduced by a bank, then these templates have to be updated. So very inflexible and very costly. The proposed approach that my group suggested was that let's just consider this as a statistical hypothesis test. Either the note is genuine or it isn't. And this will be a sequential test. So we would be keeping up, we would keep updating the model underlying the hypothesis test. And what that means then is that our template is statistical, and it means that it can be adaptive locally. Now, I could also say that this is a machine learning tool, it's going to learn adaptively and so forth, but the reality was we were working with a statistical hypothesis test. And it also meant that as far as the customers were concerned, the banks were concerned, depending on how much they valued their customers, so if a customer had inadvertently been passed some counterfeit currency and they tried to deposit that in the bank might not want to upset them by declining to accept their deposit. And so some sort of cost with regards to false positives and false negatives was something that could be engineered into the solution in a very natural way. And of course, if new banknotes are introduced, then again we can just bootstrap the test using statistical samples. Now, what did we do? We basically looked at the colour of the money, and we designed various features and so forth. I can't tell you too much, but there was a number of various features that we did look at. What did we do technically? We didn't use deep learning. We didn't use any machine learning. We used really cool and trendy statistics from the 1930s, which incidentally most data scientists actually are using as well. Right? Clustering has been around for a very long time. We used classical hypothesis testing, nothing else. Okay, we had to be a bit clever as to, let me just quickly remove that before someone takes a photograph. No, I'm only joking. We basically used mixture models to represent the characterization of the banknotes. We then got really trendy and moved from the 1930s to the 1980s, and we used some really cool optimization theory, where we basically, what we wanted to do is improve the power of the test, and we looked at segmenting the images of the notes into various regions, and then optimizing the tests that were done in each of these regions. So again, nothing terribly cutting edge here. This is all stuff you can find in textbooks or certainly well-established papers. Eventually we published the work in a little paper, and a number of patents were applied for and then subsequently awarded. And one of my postdocs that developed the methodology was actually hired by NCR to develop technology. Okay, so from the actual research to proof of concept to then going through the complex procedure of developing technology that was going to be sufficiently robust to be deployed by a multinational company whose products were going to be deployed worldwide. And it was absolutely fantastic to see. So of course I just went back to my day job of doing research that very few people are interested in. But it was really interesting to see this technology develop across the technology readiness level, the TRL chain. So from basically a published paper right through to what is now a currency validation service that NCR offers as an add-on to their current products. And in fact, within the UK, the Royal Bank of Scotland actually uses this in their ATMs. So this is a great example of how, and of course, the solution is completely data-driven. The template is driven by data. So the data, each data point being a very cheap and cheerful image of a banknote, right? And the whole solution is based on how we manipulate that data and get as much information from that data, and then how we make decisions based on the information and the evidence provided by that data. And we're basically replicating this with all of our partners. And I want to just, while I'm talking, play this little video because I mentioned this. How do I do this? Yeah, good. The data-centric engineering program at Turing are now leading on this project with a company called MX3D, who have basically developed a way of 3D printing steel and making structures Initially, they started off with furniture and art pieces that would be deployed and would be housed in art exhibitions and so forth. And then they said, we're going to build a bridge. And we're going to build a bridge across a pedestrian walkway in Amsterdam, and this is going to be, something of real civic pride for the city. Printed bridge. So we got involved because printed steel really frees the designers to come up with beautiful, schemes and designs like what you've seen here. Unfortunately, we don't know what the material properties of printed steel are. We don't know what its Young's modulus is. We don't know how uniform it is because the whole process is being run by robots. And so we needed to basically develop a living laboratory where we would sensor this structure and continually generate data from it, observing how it responds to the changing weather, the changing usage, how many people are on it, whether they're jumping up and down or whatever. Furthermore, maybe I'll just play it again while I'm doing more chatting. So as far as I see, I've been talking for 20 minutes. Yeah. So I've got another 5. Yeah. The other thing, of course, is developing what's called the digital twin. And this is, in essence, a mathematical representation of this structure that combines all of the data that we're collecting from the actual structure to refine the mathematical model. And I think this is another really exciting area of data science that maybe doesn't get as much coverage at present, but I think in the future it will, where we're taking mathematical models and data and melding these together to give us something that neither the data alone can provide nor the mathematical representation or model. And I think this is really exciting. It's incredibly cutting edge, and we're very excited about this. So as I said, the Times are going to be running a story on Monday about this, and we're hugely excited. We're also working with more traditional, what I would call data science applications, where you can instrument a gas turbine and then assess its health from that. And by assessing its health from the data from all of the sensors on the turbine, we could then predict when the machine, the turbine, should actually be taken out of service and perform some maintenance on it. This is not a straightforward problem. Here's another example where data is actually generated from a computer simulation. So here we were asked by the food industry, you've all heard of computational fluid dynamics, and you really need to have a PhD to be able to run any CFD codes. And what they wanted was their process operators in their factories to have a tablet. And what they would do is they would be able to say, okay, this is Cadbury's. We are currently pushing milk chocolate through these pipes. We want to flush the pipes, and we want to run some, I don't know, dark chocolate or some exotic type chocolate for the next production session. Well, you can see how the chocolate would be flushed through if you run some CFD codes. But you're not going to be getting any of the technicians doing that. But if there was a tool that basically just had a number of dashboards to say, I want this amount flushed through by the end of shift, then the data from the CFD simulation could be used to represent what settings the technician would have to set on the machinery and so forth. So this is something that we're again working with alongside the food industry. the sort of plans that we've got for the program, we've got an international expansion, we've got a network, we're growing the program, we're going to be training data-centric engineers. If data-centric engineering really is a thing, then we need to train the next generation of engineers, both in data science and in statistics. So, is this hyper hope? Well, I would say that data-centric engineering is nothing new, and we probably won't be talking about it in 5 years' time. We'll be doing it, but we won't be talking about it because it will just be part of what we, part of day-to-day business. And this nexus of mathematics, statistics, computing science, engineering science, practice in the professions, it's extremely exciting, it's extremely invigorating. It's certainly not a fashion, and many of the major engineering corporations are really demanding data-centric trained engineers, and they're acknowledging, much in the same way as data science is, that it is a disruptive force in many of the engineering professions and the sectors that they operate in. So the potential for impact is huge, the added value is enormous, and doing this at Turing, within the data science framework, is absolutely the right place to be. So thanks very much for the T-shirt, and I think I've managed to keep to time. So.
We've got time for a couple of questions.
Yes.
I know you mentioned how you use very simple, or at least relatively established statistical models. Did you experiment with any deep learning or those sorts of things, or was it more than enough to do?
That was more than enough. Deep learning is great for various classes of problems, and my maxim is use the best tool given the constraints and the job at hand. And so, what we cooked up, can be put on a really simple, silicon footprint, because you're just keeping these summary statistics and so forth. So we really didn't, in this application, we didn't need to deploy deep learning. So we're working with the nuclear industry, looking at crack formation in graphite cores, and there we are deploying deep learning. Because engineering the features is it's a black art, so we might as well give it to a black box to engineer those features.
It seems a little bit surprising that colour was sufficient. It seems a little bit surprising that colour was sufficient.
What was sufficient?
That just looking at the colour was sufficient.
No. So colour was one of the features. There was a number of other things,
Okay.
but I can't tell you what they are.
I was wondering
NCRs.
whether you looked at sort of different parts of the spectrum rather than sort of your standard green, red, blue.
Yeah. There were three narrowband color sensors that were used, but there were a number of other sensors measuring other things that all were combined into the pot. And also, of course, you got a big piece of information from the video outside the ATM as well, and so forth. So there was a lot of information actually embedded into it. But the initial proof of concept was looking at color and then some other physical attributes.
I guess what you're talking about just now talks about the tension between industry and patents and research in industry versus research in academia and open research. Could you talk about a little bit about how you see that?
Certainly. So my own research, as I said, is probably read by about 2 or 3 people normally. And so my bread and butter is based on, publishing, academic publishing. However, I think it's very important to do research that can move very swiftly through the TRL chain. And the reason that I say that is because research that's motivated by a problem like that can actually, bring to being some really deep theoretical analysis. And if I give you one example from my own research, so this didn't really, generate anything terribly innovative or deep. The solution was really cool. And it was really cool that we could rely on 1930s statistics to solve the problem to such a level that a commercial service is actually being used now and money's being made on it. But I also worked with some clinicians who were they were looking at using data to try and understand what types of experiments based on cell lines they would have to do based on some sort of hypothesis. In particular, what they were looking at was how effective would a particular cancer type or a cancer drug be, okay? And they had some pharmacokinetic, pharmacodynamic models which they were using, and as a statistician, I said, well, we need to make sure that you know what the uncertainty is in these predictions before you start spending money on doing experiments. And the problem was so complex, right? So the statistical inference problem was so complex that the standard toolkit of numerical computation, Markov chain, Monte Carlo, just didn't work. And over a period of about 3-4 years, we ended up having to go back and really sit down and think about how do these things really work? And we ended up, drawing on Hamiltonian dynamics, Langevin type diffusions, Riemannian geometry, and pulling all of that together in a completely innovative way to solve this problem. And that work, actually I presented it here, it was a red paper at the Royal Statistical Society, has now generated a whole new area of foundational research. It's also given tools to practitioners to attack problems that they've never been able to consider before. So I'm a great believer that practical. I'm not a snob when it comes to the type of research that I do, because I think there is a payback on both levels. Now, I could go on about the tension between these two, and it needs a lot of careful management. With NCR, everything worked fine. NCR actually, they funded my PhD. Unfortunately, my PhD was pretty useless to them commercially, so they let me publish as much as I wanted. They then subsequently, about 10 years later, funded a PhD student of mine based on this work here. And the student did some things that were incredibly important commercially. And they basically said, this student can't publish anything in this work. And I don't even want you talking to anybody telling them that you're doing this work for us. And so this student couldn't publish. And this student wanted to follow an academic career. And so managing that situation, managing the expectations of the company who are paying for the intellectual property, and for the people that were actually doing it, so the student who wanted to publish, that really, that's quite a challenge. We got through it, but these are things that have to be worked out.